today's lecture is about problem 10.35. This is a design related problem which will take pretty much time to solve it. So it will be better to use spreadsheet for its solution, but you should also know how to manually solve such type of problem. A hard-on steel spring wire is used to manufacture extension spring, and it is designed for a static load of 18 lbf, and because of that load it will extend by an amount of 0.5 inches, and this factor of safety for the hook under bending will be 1.5. Hooks is full coiled and the number of turns in the body should be less than 30. Integral and half integral body turns should be manufactured if and only if it is very necessary. Otherwise it should be avoided because it will increase the cost of the spring. So we will have to design the spring for 18 lbf load, and deflection Y should be 0.5 in the spring, and the factor of safety in the hook critical position should be 1.5, which is under bending stress, and this R1 is half of mean coil diameter. This R2 is equal to 2 into diameter of the wire, and NB should be less than 30. Now to start the solution, what you will have to do is to assume the value of the wire diameter, and that value should be assumed which will be available with you as a manufacturer, and using that wire diameter find out the ultimate tensile strength, which is represented by SUT, and that is equal to A divided by D to the power n. The values of A and M can be found from table 10.4. For hard-on wire, M value is 0.19 and A is 140 kpsi dot inch to the power m, and relative cost of the wire is 1. So putting these values in the formula, SUT is equal to A divided by D to the power m, and we will get ultimate tensile strength to be 234 kpsi. These two values are taken from table 10.5. This is the hard-on wire for which these are the values of E and G. Since we consider D is equal to 0.067 inches, which is in this range, so E will be 28.6 megapsi and G will be 11.5 megapsi. So note down these values because it will be needed in the design of the spring or problem solution. Actually, we want to find out the factor of safety in S, which is equal to SSY divided by tau. It is also equal to SY divided by tau. The above formula will be for the body and critical position B, and the second formula will be for critical position A. Now let's find out this torsional yield strength and this SY. SSY is equal to some percentage of SUT, and this SY is also equal to some percentage of SUT, but both the percentages will be different. These percentages can be found from table 10.6 for the body. In fact, all the percentages can be found from table 10.7, but table 10.6 is also used. So let's use table 10.7. These are the values for hard-on wires. This 75% is for end under bending, which is point A, and this 40% is for position B because it is under torsion stress, and for the body we can use percentage from 45 up to 50. So we will take this one. So for the body, torsion yield strength is equal to 0.45 of SUT, and after putting the value we will get SSY equals to 105.3 kpsi, and for critical position A that percentage was 0.75. So SY is equal to 0.75 into SUT. After putting the value of SUT, we will get SY equals to 175.5 kpsi. Now factor of safety at point A is equal to strength of the spring SY divided by sigma A, which is the stress because of the exerted load. SY value is this one, and sigma A is equal to F max into Ka into 16 C divided by pi d square plus 4 divided by pi d square. This wire diameter D is equal to 0.067 inches and F max is 18 lbf. This C and Ka value needs to be found out, and C is equal to mean coil diameter divided by wire diameter, as R1 is equal to mean coil diameter divided by 2. So if you bring this 2 on this side, then 2R1 or 2R is equal to mean coil diameter D. So instead of capital D we can write 2R1 over here and divide by wire diameter, and 2R1 divided by wire diameter D is equal to C1. So C1 is equal to C. Now this guy is equal to 4C1 or 4C square minus C minus 1 divided by 4C into C minus 1. Sigma A or stress at critical position A is equal to this. Now factor of safety at this point is equal to SY divided by sigma A. So sigma A is equal to SY divided by factor of safety NA or NY. Now put the value of Ka in this equation and rearrange this equation. So we will get this equation. This is the value of Ka, and this F max is divided to the right side of the equality, and this pi d square is multiplied onto the right side of the equality. Now take this 4 common from the left hand side. So 16 will become 4 and this 4 will become 1. Now cancel this 4 and this 4 with each other. This c and this c will also get cancelled out with each other. So after rearranging, we will get 4c square minus c minus 1 is equal to c minus 1 into pi d square sy divided by 4 ny f max minus 1. Now bring this whole term to the left hand side and multiply this term with c and also with minus 1, and then take this c and this c common and then divide this whole equation by 4. So 4c square will become 1c square. So we will get this equation. As ax square plus bx plus c is equal to 0 can be solved with quadratic formula, which is x is equal to minus b plus minus under root b square minus 4ac whole divided by 2a. This exponent of c square, which is 1, is a, and this whole term, which is exponent of c, is b, and this term is c. Since a is 1, so remove this a from here, because 1 multiplied by the term will remain the same. As this term is equal to b, so put this over here, and this term is equal to c, so put it over here. So for the value of c, we will get this formula, and since value of c cannot be negative, so take the positive root. D is equal to 0.067, not 5, it's 7. Sy is 175.5, ny equals to 1.5, and this f max is equal to 18. So put all these values in the equation. We will get c is equal to 4.59. As c is equal to mean coil diameter divided by wire diameter, so mean coil diameter is equal to wire diameter into c. C is 4.59 and d is 0.067. So mean coil diameter will be 0.3075 inches. Now let's find out number of active coils, which is equal to d to the power 4g divided by 8 k capital D cube. All other values are known except k, and it is equal to F applied minus initial tension divided by deflection y. This F or F max is 18 and this y is 0.5. Now let's estimate this Fi, for which the equation is given in the book and we have discussed it in the theory lecture as well. This is that equation. Wire diameter is 0.067 and this mean coil diameter is 0.3075 and C is 4.59. So putting all these values, Fi equals to 6.505 lbf. For simplicity purpose, let's take it 7 lbf. So K is equal to 18 minus 7 divided by 0.5. After the calculation, it will give you K equal to 22 lbf per inch, and put this K in NA and this D is 0.3075. This G was 11.5 from the table and this wire diameter is 0.067. So putting these values after the calculation, you will get Na is equal to 45.28 tons. Now let's find out the number of coils in the body. Nb is equal to Na minus G divided by E. Na is 45.28 and G is 11.5 and E is 28.6. So putting these values, you will get Nb is equal to 44.88 tons, which is greater than 30. And since in the problem statement it was given that the number of tons in the body should not be greater than 30, so stop the problem over here for wire diameter 0.067, because it is not satisfying the condition of NB, and start solving this problem for another available wire diameter, but that may also not satisfy this condition, because of which we will have to go for the third wire diameter. So the problem will become very lengthy. That is why in the start I told you to use spreadsheet. If a specific wire diameter satisfy this condition, then what we will have to do next? So to understand that, we will go with the same wire diameter, which was 0.067 inches, and further solve this problem. So if any wire diameter is satisfying the condition, NB should be less than 30. So you will do the remaining upcoming steps as well. But if the condition is not satisfied, then go for any higher wire diameter until the condition is satisfied. Even if the condition is satisfied, do this calculation for another diameter also, and after that another wire diameter, means do it for as many diameter as possible. And when you get the solution and the data for different wire diameters, then pick the one with the best solution and best design. So let's find the free length of the spring, which is equal to 2c minus 1 plus nb whole and 2d. Nb is 44.88 and wire diameter is 0.067 and c is 4.59. So putting these values, it will give you L naught is equal to 3.555 inches. Now when you apply 18 lbf force, it will extend the spring to some length L, which is equal to L naught plus y, and L naught is 3.555 inches and y is 0.5 inches. So L is equal to 3.555 plus 0.5, it will give you 4.055 inches. Now let's find out the stresses in the body, and for the body, tau is equal to kb into 8fd divided by pi d cube. This kb is equal to 4c plus 2 divided by 4c minus 3. C is equal to 4.59. So putting the value of C, it will give you kb is equal to 1.326. Put this kb value over here and this f value, which is 18. And this mean coil diameter is 0.3075 and wire diameter is 0.067. So it will give you Tom X in the body is equal to 62.1 kPSI, and fixed torque of safety in the body is equal to SSY divided by Tom X, and this torsional yield strength was 105.5 and Tom X is equal to 62.1, so NS is equal to 1.7. Now let's check factor of safety at critical position B, where torsion will occur, and for that tau B is equal to Kb into 8FD divided by pi d cube, but this Kb is different than the Kb for the body, and this Kb is equal to 4C2 minus 1 divided by 4C2 minus 4, and this C2 is equal to 2R2 divided by wire diameter D, and in the problem statement R2 was given to be 2 times compared to the wire diameter, so put R2 is equal to 2D, dd will cancel out each other, so C2 is equal to 4. Put C2 is equal to 4 in this equation and it will give you 15 divided by 12, and after calculation Kb is equal to 1.25. So put here 1.25 and F is equal to 18, D is equal to 0.3075 and wire diameter D is 0.067. So torsional shear stress at critical position B is equal to 58.5 at kPSI. So factor of safety in S at critical position B is equal to SSY divided by tau B. This was 105.3 and this is 58.5 at kPSI. So putting these values, it will give you NS or NY at point B equals to 1.8. Now we can find out the form by this formula, which is equal to -1 into pi square d square into NB plus 2 into mean coil diameter d divided by 4. Wire diameter is 0.067 and NB is 44.88 and mean coil diameter is 0.3075. So putting these values, it will give you -0.16. As I already told you that NB is greater than 30, so it is not satisfying the condition, so we should go for another wire diameter of higher value than this, and that can be 0.072 inches, and solve the problem for 0.072 inches wire diameter. Like first find out the value of A and M from the table, and then find out the value of SUT using those values, and then find out SSY and SY from SUT and table 10.7 for percentage. Then find out the sigma A value, from which find out the value of C1 or C, from which you can find out the mean coil diameter value, and after that find out initial tension Fi, after that find out K value, and then find out number of active coils in A, from which find out the value of NB, which should be less than 30. If it is greater than 30, then leave that wire diameter and go for another one and go through the same process. And if NB is less than 30, then find out the factor of safety at the body and also at the point B. Now let's see the spreadsheet solution. These are the things that need to be calculated, and these are different wire diameters which were assumed initially to solve this problem. And as the condition was given for number of coils in the body, so these are the values of NB. If you see, NB for wire diameter 0.067 is not satisfying the condition, so this wire diameter should not be used for constructing the spring. All other wire diameters can be used for spring construction, but you will have to select the best one which have less cost and good factor of safety.